Welcome to this sixth lecture in the Structural Dynamics course, and today we're going to look at let's call it an in-between lecture, because it is not directly associated with vibrations, but it's something that we're going to use extensively in the rest of the course, namely a discretized structural model, and we typically do that by using so-called finite elements. It's not finite elements in the classic sense with isoperimetric interpolation. We will consider structural finite elements, finite beam elements, finite cable elements. So it's an in-between method to discretize structural elements instead of basic finite elements with isoperimetric formulation. The outline is that we will again start with cables, like we did in lecture number 5 concerning separation of variables, simply because the partial differential equation is somewhat nicer and easier to address, and we will have simple linear shape functions for this case. And we'll of course look at a short example, how do natural frequencies evolve for cables, before we then attend the finite element formulation for associated with beam vibrations. And at the end, of particular interest will be to merge the beam element with basically a bar element, whereby we combine a beam transverse problem with the actual deformation of a beam, so that we get the classic 6x6 element stiffness and mass matrix for planar beam elements. Just to illustrate the efficiency of actually using beam elements compared to classical isoperimetric elements that you know from your standard finite element course, I'll give you a brief example, and hopefully I can demonstrate to you how good beam elements actually are. So consider a thin-walled I cross-sectional beam that you see in its deformed shape, vibrational shape, in the colored figure A. So actually the red part that you have down here is associated with large deflection, so the more red, the larger the deformation. In figures B, C, and D, you can see some of the basic deformation shapes. In B, you will have the transverse deflection. In C, you will have the torsional angle around with respect to the center line, and because it is a thin-walled beam, there will also be some warping deformation, and that is here represented by the gradient of the torsional angle. And what you see by the red circles are actually the average values over as a given cross-section by the full 3D finite element method with the discretization that you can see in A. And it's important to note that this is actually an expensive calculation to find a single vibration shape for such a model. There are many degrees of freedom, and it's fairly expensive computational-wise to solve a full structural problem using standard finite elements. So therefore we are of course looking for effective and cheap beam elements, and that is of course the essence of today's lecture. And we add in 31 elements along the beam, and for each beam there will be 6 degrees of freedom. So there's an order of magnitude in difference in computational time between these two models. The result for the red dots or circles you'll be able to see in the figures, and on top of these figures you'll have a black line coinciding with the exact full finite element solution. And this black solid line is then the result obtained by the beam element. So this just demonstrates to us how effective developed beam elements actually are to represent the vibrations of slender, in this case beam structure, but cables and bar elements and even plates can be modeled by more structural-like elements. We will initially consider the finite element formulation for a cable element. And as we demonstrated in lecture number 5, the extension or the modeling of a cable is similar to the modeling of a bar. You simply have to replace H by EA, and of course for the finite element formulation of cables, we will have the well-known partial differential equation with a first term, the stiffness term, governed by the tension force in the cable, in the taut cable. The second term will represent the inertia, where m is the mass per unit length, and we might have some external loading. If we were to analyze a bar element instead, we will of course just need to replace h by its actual stiffness EA. Mass per unit length could for the bi-element be represented by the density times the area, and we will also have some actual loading instead of the transverse loading for the cable element. In the following, we'll simply entirely rely on the cable element, and please do the substitution yourself for the bi-element if that is needed. The way we're going to handle the partial differential equation for finite element modeling is that we're going to transform the strong form, that is the governing differential equation, into a so-called weak form, that is the symmetric form of a virtual work formulation. So first we're going to multiply the left-hand side by a virtual test function. That will be v tilde, and then we're going to integrate the equation of motion, this work equation. We're going to integrate that over the length of the element. If we're going to do that, we can see the work equation in equation 6.3, where we have the test function v tilde, and inside the curly braces we simply have the strong form equation from 6.1. So that this will be the strong form equation that we get from equation 6.1. And the integral of 0 is equal to 0. So 6.3 is now a work relation instead of a force relation. Now, we would like to have symmetry in the order of differentiation with respect to the spatial x-coordinate. For the last term, that will simply give us the loading on the structure. For the intermediate term, this will give us the inertia distribution of the structure, and we see that both the tilde function and the real solution v are both not differentiated with respect to x, so we have symmetry with respect to the spatial coordinate x. However, for the stiffness term, we see that the actual displacement function is differentiated twice, whereas the test function is not differentiated. So we need to bring the first of the three terms into symmetric form. And this we do by integration by parts. If you are in a more complex finite element form with multiple dimensions, you will not use the integration by parts approach. You'll simply use the divergence theorem, which is the extension of integration by parts to multiple dimensions. But we have a single 1D element, so we can rely on basic integration by parts. So what we do is, if we integrate by parts, we take one of the derivatives on the second factor, that will be the d dx in front of the parenthesis, and integration by parts will simply move that to the first factor, in this case the test function. Thereby we have symmetry in the order of differentiation between v tilde, our test function, and the actual displacement v. This comes at the cost of a change of sign in front of the integral and a boundary term where we add in the non-differentiated first factor and the integrated second factor. Look up any mathematical handbook on integration by parts. Then we remember that the derivative with respect to x we write by prime, and the derivative with respect to time we express by a dot. And thereby the expression in 6.1 can be written in its final form, where we have collected both loading terms on the right hand side, whereas we maintain our internal forces and our inertia forces on the left hand side. And please note the symmetry in the stiffness term, in this case associated with tensioning of our cable. What we will do now is that we will interpolate between nodal values by some kind of polynomial representation. So consider that we know the value of the cable displacement at a particular node 2, and we know the displacement at a adjacent node number 3. Then we will simply assume that in between these two nodes we will have some assumed displacement form, and this should be the lowest displacement form that will allow us to represent the internal forces. And since the since the since the shear force or the transverse force is proportional to the derivative of our transverse displacement, then V must be interpolated at least by a linear function to obtain a constant Q force throughout our cable. So we take our cable and we divide it into n, in this case, equal elements. We don't have to do that, but in principle it's nice and easiest to do it that way. They are connected by nodes, and if we need n elements, we will in this case need n plus 1 nodes. Then we assume that the cable motion can be represented by nodal transverse displacements, and these transverse displacements are then functions of time. So please note that the solution to our transverse displacement Vx of t is actually given by separation of variables. So we use a displacement function n to take care of the spatial representation, whereas nodal values represent the temporal dependency. And then we simply sum over all shape functions. That means we can represent shape functions in a large row vector, whereas all the nodal displacements we can collect in a corresponding column vector. So the column vector is represented, or the entries of this column vector is the displacement of node 1, the displacement of node 2, the displacement of node 3, all the way up to the displacement at n plus 1. And the corresponding shape functions are then denoted as n1, n2, n3, all the way up to n plus 1. We will as well represent the test function by the same interpolation, now with the nodal vector containing the displacements of the test function. And since the test function is a scalar function, it can be written by its transposed values, so it can be v tilde transposed times the shape function vector transposed. Now we substitute the representation of the test function as well as the representation of the actual displacement function into the final weak form derived here in 6.5. If we do so, then we can actually take the displacement, the v tilde function, outside the integrals on the left hand side, and on the right hand side we can take the actual displacements outside the integral, and what is left for the integral we refer to as the stiffness matrix and the mass matrix. And for the loading we also obtain an integral for the distributed part of the external loading. For the stiffness matrix, what is left inside the integral is the tension force, and then the first order derivatives of the assumed shape functions. And the reason why we have the first order derivative is that the transverse force of the cable is associated with the first derivative of the deflection. For the mass matrix, we do not have derivatives of the displacement of the interpolation functions, simply because mass inertia is associated with the motion of the cable and not its deformation. And finally, the loading, the distributed loading G, is distributed to the nodes by the shape functions via this integral, the last integral in 6.1. And remember, if you have nodal loads on your structure, you can add them directly because of the boundary terms obtained by the virtual void principle. It is important to note that both the stiffness matrix and the mass matrix are symmetric because both shape functions are differentiated by the same order. For the mass matrix that's kind of implied, but for the stiffness matrix that's not always trivial. And always remember to create this symmetry by integration of parts. In the weak form equation in 6.9, the 0 on the right hand side can be satisfied in two ways. Either the test function is equal to 0, or what is inside the curly braces is equal to 0. The test function should be able to attain any value that we like, and thereby it cannot be bound to 0. Thus, what is inside the parenthesis must be equal to 0, and that directly gives us the standard form of our discretized finite element model with the mass matrix times the acceleration of the nodal displacement vector plus the stiffness matrix times the vector displacement vector, and that should balance the load vector given by G on the right hand side. For us to be able to do simulations, we of course need two initial conditions to start our simulation. We will have boundary conditions, kinematic boundary conditions, that are required to fix our structure if our structure is not moving. And then of course the accuracy of our solution depends strongly on the number of nodes that we add. The more nodes, and thereby the more elements we include, the better our representation. However, the more nodes we include, the larger our computational effort will also be. So often we need some kind of discretization or meshing that is suitable in size, and we often do a so-called convergence analysis. So the idea to find the right amount of elements to capture exactly the number of modes and the solution we're looking for is crucial, since too many modes and too many nodes will mean that we spend too much time on each computation, and time is equal to money. We haven't really dealt with how these shape functions will actually look like. In the format that we've presented until now, we are in general in the global format. That means for a given node j-1, we will activate or require a shape function that provides a linear interpolation to the two adjacent nodes at j-2 and j. And this shape function that is equal to 0 at all other nodes, but is equal to 1 at the specific node we refer to as nj-1. That means the index refers to the node that is equal to unity, whereas the shape function must be 0 at all other nodes. For the next node at j, we are then formulating the shape function nj, and this should have a linear interpolation to the two adjacent nodes at j-1 and j+1, whereas it should be 0 at all other nodes. In theory, these shape functions will then be assembled in the n displacement vectors n, or in the displacement vector n, and then we will differentiate that to get k. But it is much more convenient and custom to make a summation over all elements, whereby we will not have large shape functions that cover the entire structure, but we will provide local shape functions for a given element. And this would, in our case, for example, represent an element from node j-1 to node j. And as we see, the only two non-vanishing shape functions for this element will be two linear functions, one with an inclination in one direction and one with an inclination in the opposite direction. The first one has a unit value at the first node, whereas the second has a unit value at the second node. And these linear shape functions we will add to this local NE interpolation function, and that means we have just as many different interpolation functions as we have elements, and we will then derive an element stiffness matrix and an element mass matrix. And then we will simply place these matrices at their appropriate locations in the global mass and stiffness matrix. And that we will demonstrate. Mathematically speaking, we can simply write that up by a transformation matrix A that is multiplied onto the local matrices from front and back, and this transformation matrix could as well rotate from a global or from a local to a global coordinate system. But otherwise, it's a fairly simple Boolean array. Let's have a look at a cable element. For cable element, we will have between two nodes I and j with respective displacements vi and vj, we have one shape function that is unity at node I, and therefore it is referred to as Ni, and the other one has a unit value at node J, and therefore it is referred to as Nj. So the element interpolation function for this element with 2 degrees of freedom is then given as the shape function for the first element, and the second entry will be the shape function for the second entry. If we assume that the x coordinate is 0 at the left node and L at the right node, then Ni will be 1 minus x divided by the length of the element, whereas Nj will be simply x divided by L. And these two expressions are shown by the shape functions in this figure here. If we remember the virtual work equation, the mass matrix will be the integral over the length of the element, then it will contain the mass per unit length, and then it will be the element shape function transposed times the element shape function itself integrated over the length of the beam. And that means that we will, inside the integral, have a 2 times 2 matrix, and this is shown for the mass matrix at this location here, where you can see that the II index upper left will be Ni multiplied by Ni, the bottom right will be Jj, and the two off diagonals will respectively be Ij and Ji, and thereby this matrix will by default be symmetric. Let's have a look at, for instance, how we could calculate this upper left component of our element mass matrix. So let's look for the element mass matrix and element 1, 1, or this will be equal to mass. We can take that outside the integral because it's constant. Then we have the integral from 0 to L, and inside we have the first component of our element shape function vector multiplied by itself, and then integrated over the length of our cable element, not the entire cable, but in this case the element length, and then we integrate that. So we take m and we take the integral, and then we add in 1 minus x divided by L, which is the shape function for the first component of our shape function. And this should be multiplied by itself, dx. It's often convenient to introduce a non-dimensional coordinate as x divided by L. That means that the integral increment dx is equal to L ds. If x is equal to 0, then s is as well equal to 0, just to take care of the boundaries. If x is equal to L, then s is equal to unity. So the 1, 1 component of our mass matrix is then equal to the mass, and then we have an L from dx, which is now ds times L. Then we integrate not from 0 to L, but from 0 to 1, and then we have 1 minus s times 1 minus s ds. So we can take ml, and then we can do the integration, but before we do so, let's just take all terms. So we have 1, then we have plus s squared, and we have minus 2s ds ml, and now we do the integration. So we get s, then we get plus 1 over 3 s to the power 3, and then we have minus 1/2 times 2, that's unity, s squared, from 0 to 1. We substitute in the boundaries. The lower boundary at s equal to 0 will not provide anything, all 3 terms will be 0. The upper boundary will give 1 plus 1/3 minus 1, and we'll have 1/3 m and then L. Exactly the value that we have at the 1, 1 element, but 2 divided by 6 is the 1 over 3 that we have just derived. And we'll have the same value in our case for the 2, 2 value, and the 1, 2 values will then be half as large as the diagonal values. If we want to just check whether we have got the stiffness matrix correct, we must then initially find the derivatives of the shape function. Simply because the stiffness matrix, let's again take the upper left component, 1, 1 component, will be the stiffness, or the tension force, and then we'll integrate over the length of the element, and we will now have the first derivatives of the respective shape function entries. And we should remember that first entry, differentiated with respect to x, is then 1 minus x divided by L, and this will simply be constant and equal to minus 1 divided by L. So if we substitute that back into the integral, we'll have minus 1 divided by L squared, and that gives us h divided by L squared, and then the integral from 0 to L dx. Remember that there's a unit value in here, so if we integrate that, we'll get x from 0 to L, and that means the solution will be h divided by L. And that is exactly the value that we get at the 1, 1 entry of our element stiffness matrix. Now we need to assemble all the elements that we have in our cable model. And let's assume that they all have the same length. The cable is homogeneously discretized by n elements using n plus 1 nodes. So let's have a look how the total matrix, the total mass matrix or stiffness matrix, can be assembled. The local mass matrix, the element mass matrix, will be equal to 1 over 6, and then we'll have the distributed mass times the length of the beam, and we'll have 2, 1, 1, 2. So the cable has its first node supported, and then we add in nodes along the way until the final node is as well supported. For the first element, the red element here, we will then offer the entire model. We'll build up a mass matrix. Let me add in a large matrix here, and at the top left corner we'll then include the matrix, and if we have a common factor outside that is equal to 1 over 6 ml, then we will here simply add 2, 1, 1, and 2. Then we add the contribution from the next element, which is green. And the red and green elements overlap at the common node. And that means that the next element should include the last node from the previous element and then adding an additional node. And because we add contributions, we should have plus 2, 1, 1, 2. Then we could have the third element, that would be the blue element. Have a common node. That means next element should overlap with the previous element and add as well a factor of 2, 1, 1, 2. So the principle is then repeated until we end at the last element, which is then the black element. So we have for the black element at the end, we add a plus 2. We already have a 2, so there will be a value of 4, 1, 1, 2. And let's just extend this large matrix so that we now cover all n plus 1 nodes in our model. What we haven't considered yet is actually how we can implement the two support conditions. Because for the first node, the support will prohibit any transverse deflections. And the same thing will be the case for the last node. In our given mass matrix and also the associated stiffness matrix, we haven't really considered the fact that the first node degree of freedom and the last degree of freedom cannot move because these are constrained. And the way we're going to account for that is that we are simply going to eliminate the first row, or column, and first row. Thereby we implement the first support, and we also eliminate the last row and the last column. Thereby we have implemented the last support. By doing that, we now have a reduced size matrix with a value of 4 at the upper left diagonal. That is this one in here. And then we will have 1 and 1. The next one will also be 4. Then we'll have 1, 1, and we will extend the matrix until our final bottom right entry will be this 4 over here. And we'll have a unit to the unit value on top, and we'll have a unit value to the left, and those are also present in our final matrix. So instead of having n plus 1 degrees of freedom, we now have n minus 1 degrees of freedom because we have eliminated 2 out of the total number of degrees of freedom. And this is the reason why, for our next example, that we have a mass matrix that starts and ends with a diagonal value of 4, simply because the initial value of 2 and the final value of 2 have been eliminated because of the boundary conditions for our given cable model. As well, for the stiffness matrix, support conditions will remove first and last column and row, and thereby we will get a stiffness matrix with an initial and a final value of 2 in the diagonal. And we can see, or we will learn, how to find natural frequencies for such numerical finite element models. It's basically solving an eigenvalue problem, and we will get just as many eigenvalues, natural frequencies, as we have degrees of freedom, and those we order in terms of their mode number. So the lowest frequency will have mode number 1, second lowest will refer to mode number 2, and so on. In lecture number 5, we actually found the exact solution for cable vibrations for mode number 1, 2, 3, up to infinity. So what we see is a proportionality with the mode number I. And that means in the curve to the right, we will have a linear relation between the mode number and the natural frequency. Here normalized with respect to the lowest natural frequency, so that we get a unit value for the first node. If we solve the eigenvalue problem for our structure, then we actually see that we get a very good representation of the first couple of modes, but for the higher modes with larger frequencies, we suddenly see a deviation from the exact solution. And that is simply because for higher modes, we have many half sinusoidal waves in the corresponding mode shape vector, and suddenly we see that for a given half sine, we now only have 2 elements. And the rule of thumb is that you, for a given half sinusoidal wave, you should probably have no more, or no less, than 3 to 4 elements. So for the red mode shape that I've indicated in the figure, the discretization that is shown is probably a little bit too coarse to accurately represent the correct vibrations of the cable, and we see that by a deviation from the exact solution that we want to replicate by our finite element model. A final notion for cable elements is that we can also use an alternative mass matrix. This mass matrix will be referred to as the so-called lumped mass matrix. And lumping means that we simply collect for a given node J, we simply take the mass of half the element to the left and half the element to the right, and we simply add all this mass directly as a diagonal entry to node number j. So for the j entry in our mass matrix, we then simply take the entire element mass, that's ml, and add directly at the diagonal place for this element, for this node. And thereby we'll get a diagonal mass matrix. And that's computationally quite effective, in particular when we get to time integration later in this course. You'll see that we need to invert the mass matrix. And it's trivial to invert a diagonal mass matrix compared to the mass matrix, the so-called consistent mass matrix that we have derived based on shape functions, which is non-diagonal. But if we use the lumped mass matrix, we also get a good representation for the first couple of modes, and then at some stage we suddenly see a deviation as well relative to the exact solution, but instead of over-predicting the natural frequencies like we did with the consistent mass matrix, and let me just be a little bit consistent in my notation, so the green one is the consistent matrix, whereas the red boxes refer to the so-called lumped mass matrix. And the very special thing about cable elements is that if you take a mass matrix that is half the consistent plus half the lumped, then you will actually get a representation that is basically aligned with the exact solution. So there's always the possibility of mixing consistent and lumped mass matrices, and for cable elements, half-half is optimal. For other types of element, another blend will be better. Of particular interest in this course is vibrations of beams. So we would like to derive the finite element formulation for beams, especially for their vibrations. The partial differential equation we've seen before, previous lecture, it contains the stiffness term, it contains an inertia term, and then some form of external distributed loading. So W is here the transverse displacement field. We assume a bending stiffness of EI and a mass per unit length equal to rho A, and we have some loading. Of course, we need initial conditions to activate our vibrations, and we also need boundary conditions, and because we have a fourth order derivative, then we will, in principle, have boundary conditions of 4 different types, but for the finite element formulation, we will only use the kinematic boundary conditions. Either we have a condition saying that we have no displacement, like we had for the cable, but additionally, we will also have the possibility of no rotation, whereby theta, the nodal rotation, is prohibited. Again, we want to reformulate the force balance equation in 6.15 into a weak form energy balance by the principle of virtual work. We will then assume shape functions for the displacement and as well for the test displacement W tilde. And then we will simply evaluate stiffness and mass matrix for the beam element by the derived spatial integrals. We will have our strong form equation, that's the partial differential equation. We multiply that with the test function W tilde, and we integrate over the length of the beam, and that should be equal to 0. We see that the two last terms have the final form. There are no difference in the order of differentiation for the two last terms with respect to the spatial coordinate x, but for the first term we see 4 derivatives on the stiffness term and no derivatives on the test function. So we need special concern for the first term. So we write up the first term, and we will again use integration by parts. So if we do that once, we take one of the two external derivatives and we move that to the test function. Thereby the test function has a first order derivative, whereas only a single derivative is still differentiating the parenthesis, representing basically the bending moment. Of course, we then need to change the sign in front of the integral, and we need to construct the boundary term where the test function is not differentiated, whereas the second factor is integrated once. We're not finished, because in the final integral we still have asymmetry between the order of differentiation. So we still need to move the remaining derivative on the parenthesis onto the test function. And this we do by integration by parts one more time, and thereby we get same derivative on both w functions. We need again to change the sign in front of the integral, and we need to add an extra term to the boundary bracket, and we add the first factor without the differentiation, and we will add the second factor with its integration. Now, what we see inside the square bracket is actually the definition of section forces. So we see that the displacement produces energy with EI and then W double prime and everything differentiated once. This is actually the definition of the shear force with opposite sign. Then we see that minus W prime, which is equal to the rotation with our given coordinate system, produces energy with what is inside the parenthesis, and that defines the section moment with opposite sign. So if we substitute our integral back into the weak form equation, we will take the square bracket and move to the other side of the equality sign. Then the square bracket can be written as the boundary terms for displacement multiplied by shear force plus rotation multiplied by moment. And this demonstrates that shear force and moment are energy conjugated forces to the displacement and the rotation. So this square bracket term represents loads, forces, moments applied directly to the nodes of our beam element, whereas the final term, which comes from the third term in the upper equation, represents any distributed load that is then by this integral distributed to the two element nodes, referred to as equivalent nodal loads. On the left hand side, we maintain the stiffness term and the inertia term, where we in particular see that the stiffness term is now symmetric with respect to its derivatives. We see from the virtual work equation that we have defined not only the displacement, but also the rotation as our governing degrees of freedom. So we need to add both displacement and rotation as so-called nodal values. So for the cable element, we only had the transverse displacement as our single nodal value. But for a beam element, with a given node, we will suddenly both have a transverse displacement, but we will also have a typically counterclockwise rotation. Therefore, in terms of global shape functions, we will now have two terms per node. We will have one shape function that interpolates the transverse displacement, and we'll have another shape function that interpolates the nodal rotation. So these are collected nodal-wise in our n vector, as given here, whereby we can collect all the nodal degrees of freedom in terms of their nodes in the w vector. And thereby we'll get the final form of our displacement interpolation, a similar way as we got for the cable, represented by a row vector n multiplied by a common column vector w. And if we substitute that into the weak form formulation, we will actually end up with the classical finite element equation similar to that we got for the cable. To demonstrate this, let's just have a look at the virtual work integral for the stiffness matrix. We just need to get that right. Like this. Then we substitute in the expression for w tilde. That will be the shape function vector multiplied by the vector containing all nodal displacements, and that will have a tilde. Because w tilde is a scalar function, we can, like for the cable, transpose these and get the correct expression still for w tilde. Then we also interpolate w, and this we simply do by the same shape function, but nodal values are now without the tilde. Then we substitute in w tilde on the first term factor and w into the last factor, and thereby the integral will be from 0 to L. Then we'll have a vector w tilde transposed, n transposed, ei, which is a scalar, n, and at the end we'll have w vector. and everything integrated as function of x. Now, separation of variables tells us that w tilde is only a function of time, whereas our shape function contains the dependency with respect to x. So therefore, we can take our degrees of freedom vectors outside the integrals, and we will have w tilde transposed from 0 to L. And let's just utilize, in this case, that the bending stiffness is constant, organize it a little bit differently, like this, and we'll have w as function of time, which is a vector behind the integral. And this internal work defines the stiffness matrix directly from this integral, which corresponds exactly to the same format. We just need to, sorry, I forgot to get in here, let's just redo this. We need to remember to take the double differentiation, otherwise this is not correct, and let's just also correct that here. So we need the double derivative of the shape function vector like this. So the stiffness matrix is equal to, and if EI is constant, we can take that outside the integral. If it's not over a given element, then it has to stay inside the integral. And then we'll have the shape function double derivative transposed, multiply by itself, and then the integral over the length of the beam. So this will be a matrix that has the dimensions similar to the number of degrees of freedom that we have for a given element. For the mass matrix, it works exactly the same way. So we'll have, let's just put it this way, we will have the test function, then we'll have rho A, then we'll multiply by the acceleration. We will substitute in our expression for our interpolation of the displacement field, whereby we will inside the integral have the shape function, rho A, shape function again. These are vectors integrated over x multiplied by the acceleration. And this will then define the mass matrix, whereby we will have m and then the acceleration vector at the right. So both the stiffness integral and the inertia integral will have the transposed of the test function in front as the first factor, whereby it will appear as a common factor on all terms. The test function cannot be equal to 0, therefore everything within the parenthesis should be equal to 0, and that provides us with the equation of motion in its well-known form in 623. As for the cable element, the mass matrix, the stiffness matrix, and also the load will be derived element-wise and then substituted into the global mass matrix, stiffness matrix, and load vector by an assembly procedure as described for the cable element. The classic beam element has two nodes, node 1 and node 2. For the cable element, we only had transverse displacements for one for each node, giving us 2 degrees of freedom per element. For the most basic beam element, we need to add 2 rotations, theta 1 and theta 2, whereby the basic beam element matrices will be 4 by 4 matrices. The 4 degrees of freedom we collect in a column vector, first with the 2 node 1 values, and then the 2 node 2 values. And each of these 4 nodal values are associated with 4 shape functions. N1 is describing unit displacement at the left node, while the remaining 3 degrees of freedom are kept equal to 0. That gives us the N1 shape function shown in the figure here. For N2, we'll have a unit theta 1, while W1, W2, and theta 2 are kept equal to 0. N3 is a unit displacement at the second node, while N4 is the unit rotation at the second node. Look up in any finite element handbook, structural mechanics book, whatever, you will find that cubic shape functions will be sufficient to interpolate a beam problem. And the reason for that is that the section force with the highest order of derivative will be equal to the shear force, and that we need to differentiate 3 times. Thereby, cubic shape functions will give us constant shear force along the element and a linear variation in the bending moment. And that is sufficient for our interpolation. Stiffness matrix and the mass matrix are given by, we have derived by these expressions. So for the stiffness matrix, the element shape functions must be differentiated twice and then multiplied, and then we need to remember to multiply by the bending stiffness EI, whereas the mass matrix, as for the cable, is given by the shape functions without any derivatives, simply because mass inertia is associated with motion and not with any deformation. Once we have the element matrices, we put them into the global matrices by first transforming them to global coordinates and then stacking them by the assembly procedure. We need to remember to enforce kinematic supports. That means eliminating rows and columns. And at the end, we then solve our dynamic problem. And because it is dynamic, we can actually also solve problems without any supports. That will simply mean that we have some form of free motion. That could be a ship that is sailing, that could be a satellite orbiting Earth. There could be many types of structures that do not have fixed supports. In civil engineering, we would mostly expect our building to be supported by ground. The matrices, the stiffness matrix and the mass matrix given in the equation, can be derived or found in basically any textbook. I would like to demonstrate to you how it's done. And I would like to calculate the 1-2 element, both for the stiffness matrix and the mass matrix. So, element stiffness matrix, and let's just consider entry 1, 2, is then given by the integral EI, and then it is the element 1 differentiated twice. So the first entry in the element shape function differentiated twice. So this index 1 refers to the 1 index, and then the row number in the stiffness matrix. And this should be multiplied by the element interpolation component 2 differentiated twice. So the index 2 refers to the column number. And we differentiate this with respect to, or integrate this with respect to x. Let's just write down the 2 interpolation functions and do the differentiation and perform the differentiation to find the double derivatives. So first, if we go back and have a look at the element shape function, entry number 1 is shown here, and thereby written as 1 minus 3x divided by L plus 2x divided by L to the power of 3. If we're going to differentiate that once, then we'll get that the first term vanishes, next one will become minus 6x divided by L, and we need to differentiate the internal value argument function as well, so that gives us 1 divided by L. Then we'll get plus 6x divided by L to the power of 2, and again 1 divided by L, because we differentiate with respect to x and not x divided by L. And then we can finally get the second derivative, like this, by differentiating the upper expression once more. So we get minus 6, 1 divided by L squared, and the next one will have plus 12, x divided by L, 1 divided by L squared, or 1 divided by L squared, parenthesis, minus 6 plus 12x divided by L. And we immediately see that this x divided by L is equal to S. So it's nice to write it in terms of this non-dimensional coordinate S, because once we perform the integral, we will transform it into an S integral. That's the, at least in my opinion, the easiest way to do it. Then we'll have the E2, and that will contain an L in front, because it is an interpolation function that is associated with a nodal rotation at the first node. So therefore, we need an L contained in the as a common factor on the shape function. We'll have x divided by L minus 2 x divided by L squared plus x divided by L to the power of 3, and we close the parenthesis. Then we will have the first derivative of NE2. That will again common factor L. We will have 1 divided by L for the first term minus 4x divided by L, 1 divided by L plus 3. Then we'll have x divided by L squared, 1 divided by L, closing the parenthesis. Now we're almost there. Now we differentiate once more. Still have a common factor L. The first term will vanish because it's constant. The next term will give us minus 4, 1 divided by L squared. And the final term will give us 6 x divided by L, 1 divided by L squared. And we can take 1 divided by L squared outside the parenthesis, whereby we'll get 1 divided by L minus 4 plus 6x divided by L. And again, you see that this will be equal to S. Now we can take the component of the stiffness matrix. We could take EI outside the integral. Inside the integral, we will have the N1 double derivative. Let's just remember to include 1 divided by L squared. Then we'll have minus 6 plus 12x divided by L. Then we'll have 1 divided by L from NE2 double derivative, and inside the parenthesis we have minus 4, 6x divided by L dx. We will have in total 1 divided by L to the power 3 that we can have outside the integral. Inside the integral we substitute in S. That means we integrate from 0 to 1. So we'll get minus 6 plus 12s minus 4 plus 6s ds, and then we need to remember to multiply by L. That means that the common factor is EI divided by L squared, and then we integrate from 0 to 1, one big parenthesis, providing us with 24 minus 36s minus 48s plus 72s squared, integrating with respect to s. We see that the two middle terms are equal to minus, that is 84s. So thereby we will get EI bending stiffness divided by L squared, and we'll have a square bracket representing the integration, 24s minus 84s integrated, that is 1/2 times 84 times s squared, that's 42s squared, plus 72 times 1/3 times s to the power of 3, that is 24s to the power of 3 from 0 to 1. The lower boundary does not provide anything, and for the upper boundary we substitute in s equal to 1, so the two 24s will add up to 48 minus 42. That will give us 6 EI divided by L2. 6 L times EI divided by L to the power of 3 gives us exactly the result that we have just found. So that means by this procedure we can actually determine all the entries of the stiffness matrix. Remember that it is symmetric, so you need to calculate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 integrals. That's pretty heavy if none of them are trivial equal to 0, which is not the case here. So often this is done by numerical integration using Gauss integration or some other types of integration procedure, or in modern times you can also find analytical tools such as Maple or Mathematica to help you evaluate these integrals. But you're more than welcome to do it analytically with a pen on paper. Let's have a look at the mass matrix. For the mass matrix, again the 1-2 element, we'll have the integral, then the mass per unit length, then we'll have the cubic shape function number 1 times the cubic shape function number 2, integrated over the length of the beam. Let's just consider this product. And that means going back and then multiplying the n function, n1 function, with the n2 function. A little bit much forth and back, but the n function, n1 function, is 1 minus 3s squared plus 2s to the power of 3. The reason why I'm using s from the beginning is that the mass matrix is not associated with any differentiation. And the major mistake I see is that whenever we're going to differentiate and we introduce our s coordinate, we forget that the differentiation is with respect to x and not s. And then we simply miss multiplying with the 1 divided by L, as we had to do for the stiffness matrix. But for the mass matrix, there are no derivatives, and therefore we can introduce the s coordinate initially from the beginning, and that makes it a little bit easier. Then we have 2s squared plus s to the power of 3L. Now I simply multiply all terms. That will, in total, give me 9 terms. These I then assemble and collect into what appears as 6 terms for their respective order in the polynomial. And we go from the first order term all the way up to, let me just, hopefully I'll get this right, up to a 6th order polynomial term. And now I need to integrate this. So the mass matrix, I can take rho A outside and the L from the n2 function. I will also take outside the integral from 0 to L. And then I plug in this. And that will now be the integral over S. And then I need to multiply by L. And if I do so, I need to integrate from 0 to unity. So we'll simply do that. And S integrated is equal to 1/2 s squared. 2 is 2 over 3 s to the power of 3 minus 2 over 4, that is 1/2 s to the power of 4. Then we have 8, and we need to divide by 5 because s comes to the power of 5, minus, and we'll have 7 divided by 6, power to 6, and we will have at the end plus 2 divided by 7, s to the power of 7, 0, 1. And if we add in the upper limit, all the s's will be equal to 1, independent of the power, and all the lower boundaries will then make all the terms vanish. So that means it's 1/2 minus 2/3 minus 1/2 plus 8 over 5 minus 7 over 6 plus 2 over 7. And if my calculation is right, and I think it is, then I get 11 over 210 rho A L squared. Now it turns out that if we do this for all the other terms, there's a common factor, and that's not a common denominator, and that's not 210. It turns out to be 420. So outside the mass matrix we'll have 420, and then we'll have the total element mass. What is left in our solution is not 11, but it's 22, and then the element length L. And that means we should be able to identify this common factor on the mass matrix and this entry for 1.2 in our mass matrix. And that's exactly what we see, namely that we have the common factor that is equal to the element mass divided by 420, and at entry 1.2 we get 22 times the length of the element. Again, we need to do this, repeat this 10 times, in total 10 times, to get all the entries. So again, numerical tools or some nice analytical mathematical tools are a certain advantage. The final thing that we are going to consider is the augmented beam element. So in this augmented beam element, we will, besides the transverse degrees of freedom, that means vertical displacement and rotation at the two nodes, we will have to add in the horizontal degrees of freedom, and these are associated with the extension of the beam, so that means simply the bar element. And as we remember from the cable element, that requires the first order derivatives of the corresponding displacement, in this case the horizontal displacement u, and then instead of the tension force H, you should simply have the bending stiffness EI. For the inertia term, we will have the corresponding displacement and acceleration, and then the mass per unit length, which, by the way, is the same for the beam element as in the transverse problem, where we also have rho divided, multiplied by A. On the right-hand side, we need to add in the possibility of having nodal horizontal loads, and in principle, we could also have horizontally distributed loads here given by a small capital N. So by this extension of virtual work, and that's one of the benefits of using work, is namely that contributions are additive. So we can simply add the virtual work contribution from extension, and if we want to add additional effects, that could be tensioning effects, for instance, column effects, then we could also add the work from this contribution. So the nice thing about a weak form is that additional terms, additional effects, additional degrees of freedom can be added by simply additional terms. Now, on the left-hand side, we have two displacement fields. We have a horizontal displacement field, and we have a transverse or vertical displacement field. So therefore, we now have two rows instead of one. We collect the corresponding degrees of freedom in a 6x1 vector that we will refer to as Q, and we initially have the three components associated with the first node, and then we will have the three components associated with the second node. And usually we order them in by first the horizontal, then the vertical displacement, and finally the rotation. And we do that in both nodes. And therefore, the four shape functions that we already have considered for the transverse problem are shown at the bottom of this figure here, and they are in the order of the degrees of freedom, now equal to N2, N3, N5, and N6. And they should be placed at their respective entries columns in row number 2 of the interpolation array, and not interpolation vector anymore. For the horizontal displacement at degrees of freedom 1 and 4, we now have linear shape functions, as we had for the cable. So N1 is placed in the first column of our displacement array, interpolation array, and the other linear shape function that we also used for the cable is placed at number 4, so that they are multiplied with the horizontal displacement of node 1 and the horizontal displacement of node number 4. The stiffness matrix is obtained by exactly the same integral as before for the simple beam element, and the same is the case for the mass matrix. Now the interpolation functions do not have 4 columns, but they have 6 columns. So therefore, using these 6 shape functions in this format, the n function will be a 2 times 6, and thereby both k and m, they will be 6 times 6 matrices. And if we substitute in our shape function in the integrals on the previous slide, we will directly, by numerical or analytical evaluation, get a 6 by 6 matrix. However, it is actually easiest to derive a matrix entirely based on the first row, and thereafter finding a matrix based entirely on the second row, so that we split the interpolation array into two row vectors. And the reason why we can do that is that for any entry in the first row, the second row has 0 entries, and for all entries in the second row, the first row has 0 entries. And thereby we will get two separate stiffness matrices, namely a first stiffness matrix that is only concerned with the extension, whereas we will have a second matrix that is entirely concerned with the bending or the transverse problem. You can see the cable element matrix 1 minus 1 matrix placed at rows 1 and 4, columns 1 and 4. And you can see the previous stiffness matrix for the beam element, the 4x4 beam element matrix, placed up in 4 groups at the remaining entries. That means 2, 3, 5, 6, and the same for the columns, 2, 3, 5, and 6. For the mass matrix, we can do the same thing, split it up in the contribution from the axial coordinate and the corresponding contribution from the transverse problem. And we identify our 22L, and we can also see the 2, 1, 1, 2 format that we have considered previously for the cable element. So the finite element method, at least the way we consider it, is a method of reducing otherwise infinite continuous problems into discretized equations that we can solve by numerical means. And the idea is that we need to derive a mass matrix and a stiffness matrix. The stiffness matrix you probably already know from your basic statics course or your initial finite element course. Maybe the mass matrix is new to you. The essence, the theory behind the finite element is definitely the derivation of the weak form equation. So we go from the strong form differential equation to a weak form format that we make symmetric by integration by parts, and it's a condition that represents the integral over the entire structure. Remember to eliminate rows and columns so that you can add in your boundary conditions. And remember to use a sufficiently accurate discretization enough element so that you represent all your required vibration modes with sufficient accuracy. And we have seen that in particular higher frequencies are not as accurate compared to their analytical solution. So with that, enjoy.